Thanks for joining me for the graveyard shift. My name is Greg, and I've got a small talk on the merge and how it enables innovation at the consensus layer. So a little bit about me. My name is Greg, and I'm a senior software engineer at Interlay, working also on the Bob stack. We're running a hacker house this week on building on Bitcoin. And if you want more info on that, please come and chat to me. Mostly working with Bitcoin and Ethereum, sometimes Polkadot, and we have two parachains on the Polkadot and Kusama, mostly, again, also in Rust. Before I kind of get into the nitty-gritty, I wanted to kind of give a bit of motivation review why this talk came about and kind of where my stance is. So looking at the landscape circa 2019 pre-merge, we had a few different clients. Geth has always been the predominant client for ETH mainnet. With that, we have a few different consensus modes, ETHhash and Click. Some of the other variants, Nethermind has Aura, Bezu has IBFT 2.0 and QBFT. So we had that sort of the lay of the land. But then zooming out, we can see there's like tons and tons of forks. So Geth itself over the years has been forked so many times, it's just unmanageable at this point. The other clients, of course, have their own versions. Optimism has forked several to make its changes. We have different versions of EVM deployed on different chains, both as forks of Geth and re-implementations. A few of these on the list, for example, have used some common libraries. Some use Geth as a library. Some use Rust Ethereum as a library. But if you go onto GitHub, there's just so much code out there doing basically the same thing. Geth, you can see at the top there, has over 20K forks. Admittedly, some of those would be from contributors, but by and large, there's, in my opinion, too many. So yeah, that brings me to my controversial opinion. I hate forks. But not sporks. You know, this is ETHDenver after all, and sporks have utility. I do like sporks. The other thing that kind of motivated me recently was kind of Click was being removed from core Geth due to obviously all the changes required for the beacon chain and ETH2. And we had a project, which I'll discuss in a bit, which made use of proof of authority. So this kind of motivated me to kind of dig into this topic and kind of investigate the changes I'll outline soon. And what do I want? And why am I so bitter? Well, I want the ETH1 stack. I love the ETH1 stack. It's tried and tested, especially Geth. It's a classic, but we have so many different consensus mechanisms. If we're limited purely to ETHhash or Click or just whatever's running on ETH2, then I think it's a shame because there's a lot of innovation happening out there, and I think we can help that further. And then, of course, I want fewer well-maintained EVM implementations. A bug in one spreads to all of them. It's impossible to update, and ultimately, audits are expensive. So we audit one, we have to audit all of them. So let's fast forward now to the merge and the kind of tech stack that brings with us. We now have two different kind of clients. It's a separation here. So we have the execution layer. That's Geth. That's bringing us the smart contracts, the execution, the state transitions, the state management, and it's a pretty well battle-tested piece of kit. Then we have now the consensus layer. This is what's driving the execution layer now. With ETH2, we have proof of stake. That's handling rewards and penalties and attestations, and again, driving that block construction. So we have this nice wee separation. Typical example of the stack now, kind of in the spirit of Ethereum and Lego blocks. We have Geth and Prism. We have Reth and Lighthouse, because we love sticking two products coded in the same language together. And we have this thing called client diversity. Maybe that's a fancy way just to say fork, but it's nice to see different things using the same bit of kit. Throughout all of this, it's always usually Geth or Reth as the execution client, so it's nice to see some reuse there. How this works is using kind of a nicely defined interface that I think a lot of people worked on for a long time called the Engine API. And it's kind of summarized in 3 steps. Fork choice, you can call that to update the head of the chain, which block we're building on and where we're going with that, what's finalized and what's safe to produce on top of. Get payload is basically used to tell geth to, or ref to construct the block, and new payload simply imports that block. So you can see that if we kind of build a system around that, it's super easy just to tie that together and build a kind of new set of mechanisms to drive block production. This is all locally, so the engine API operates on local node, or it may operate remotely, I guess, but typically it's authenticated using JSON web tokens. And if you want to kind of a better, more rounded explanation of that, this blog here has some wonderful diagrams that kind of go into sort of the nitty-gritty of how that looks. But how, again, does this help us? We don't need to run the ETH2 consensus layer. We can, as I said, we can drive block production some other way. And then with this, we can now reuse production-ready components, as I said, like geth and ref. Although I guess ref isn't production-ready, geth is obviously well used in the community. And that, as mentioned before, handles all the transactions, state management, and EVM, and all the fun stuff. And then maybe this means we don't have to fork geth anymore. Geth can remain as it is with a nicely defined interface, doing exactly what it's meant to do. Lighthouse is one such consensus client, but it also says as a library. I didn't review Prism. I assume it can also be used as a library, but I like Rust. The Lighthouse like library or application wraps the JSON RPC API with a super easy wrapper. We can even write this ourselves if we wanted to. And we can use that to drive block production. With Lighthouse, we can also use it as a library to do some pretty other interesting things. So, for example, in our client, we're using the same BLS signature signing algorithms, and we could do aggregation and data storage. We can also reuse components from the Lighthouse as a library using LevelDB for state management. So here's a nice succinct bit of code here, basically, again, using the engine API to do exactly what I've said before. We're telling it to update the fork, build a block on it, and then import it. But we can see something at the top here. We see these things called payload attributes. And to go a bit further into that, payload attributes is just defining what we want geth to do. So we have quite obviously the timestamp. We have the random, which is accumulated randomness we need to submit. And we have two things for, I guess, printing money. As I say here, print to go burr. So the withdrawals is basically what we tell geth to mint, so to speak. And this is kind of a hack, I suppose, in ETH2 jargon, actually. This is what validators use to exit the system. If you're not familiar, in ETH2, there's a deposit contract which uses to lock up their ETH, and that's locked forever, so you never get that out. The way they get around this is by adding this withdrawal mechanism into geth via the payload attributes, so users can withdraw their funds back to the execution layer, I suppose. The one trade-off here is that the minimum precision is 9 decimals, so the interface is assumed that that's in GUI, which means if you are building a custom blockchain which needs to have a smaller representation, it's unfortunately not possible. But it's kind of hacky how we get around this, and that's just unfortunately the way it is. We also have the fee recipient. That's set at the consensus layer to tell the execution layer who should receive the fee, the block fees. Again, that's based on the genesis. So it might depend how those fees are distributed. And also with the execution to consensus interface, that interface isn't strictly defined. So we aren't always expected that that fee recipient will be the one that receives the fees. That actually may be overridden, which is why you'll often see it written as suggested fee recipient, because geth can have a configuration to override that. But typically, if you're setting up the stack locally, perhaps via the kurtosis package, those components are well defined together, and that won't be overridden. So this is kind of how we get away with kind of minting money if we were to write a new consensus layer using the execution layer, the pre-existing one rather. But the issue is then we can't inject transactions, which brings me to my next point. Opstack have forked geth. I know, I don't like forks, but they have introduced a few good mechanisms to help with this. So taking advantage of the same kind of architecture, they've added additional payload attributes. So we can see in the snippet here, they actually add transactions to be directly written to geth. We have a flag that tells the geth not to use the transaction pool. This is particularly important for the way OpStack works. It may operate in one of two modes, either in sequencing or verification mode, I guess. And in order to distinguish those, you basically tell it, when it's constructing a block via the payload attributes, not to include transactions for the mempool. So when sequencing for the layer 2 and OpStack, you tell it to include transactions, because you want to include the layer 2 transactions. But when you're verifying simply that everything submitted to the batch inbox on the layer 1 is correct, you'll tell it simply to construct with the predefined set of transactions in these attributes. It also defines a gas limit. So I mentioned this is a fork of Geth. One nice thing is Ref actually has compile flags, so no more code to maintain. It's all in one place and makes it super easy. And so I want to now just spend a slide kind of defining what we're building here on Bob and why this is relevant. So we're building a few different things. So the reason actually I kind of went a little bit into OpStack is we're building a L2 rollup with Bitcoin in mind using the vanilla OpStack. We're actually intending to add a new protocol based on merged mining to that, but right now it's just vanilla. We're also working on a layer 1 Bitcoin sidechain with a hybrid consensus mechanism, again using merged mining. This is based on current standards for merged mining, including Namecoin Oxpow. It uses a new consensus, well, an old new consensus mechanism, Aura, which you're most aware of, which I don't think works that well. So we're planning to move to QBFT soon. And in this, we use an unmodified version of Geth, which is super great because I don't need to touch anything to do with the EVM. It just works out the box, and I can focus on the consensus algorithm. And as mentioned, both of these will be merge mined with Bitcoin mainnet. One interesting challenge I came across when building the layer 1 specifically was sort of hacking fees. So we're already kind of doing a few hacks with the withdrawal mechanism, but we actually did have an additional challenge which I would like to summarize. So we had a requirement that with the merged mining protocol we were working on, that the fees were distributed to the miner when they submit the Oxpow. So not as with the payload attributes, it's intended that each block you generate, you set the fee recipient, and they receive the fees from that block, rather. So that's the problem. And how we got around this was actually to burn all the fees. So on each block construction, we would send all the fees to a burn address, some contract or the dead address, I guess. And then what we would do on block construction is actually then fetch the receipts. We would accumulate the fees and track those, and then re-import via the withdrawal mechanism. So it's a bit of a hacky workaround, but it worked for our use case. And to sort of summarize my personal views, again, too many forks. I think I've not said this enough. I hate them, and I want everyone to use more well-written code and like the same code. There needs to be more cohesion. Development in general, I think, on Ethereum is limited to the ETH2 effort. Innovation is happening at smart contracts, and I really want to see more innovation happening further down. So this is why kind of my outlook is to make it easy to build new maintainable L1s. I want people to work on new consensus algorithms just as we have, using tried and tested components like Geth or Ref, and go to market with that. Ideal would be if there exists a toolkit such as Substrate for Ethereum that could allow developers to quickly spin up a new network, again using Ref or Geth, and just work on the consensus. I finished with a bit of time to spare, which is great. Thanks for listening. My name is Greg. Please follow me on X, I guess, or Telegram. And we're hiring. So if you want to work with Layer 1 consensus on Ethereum, please either speak to me after the talk or scan this QR code. And it was great to talk to you. Thanks again.